in the previous lecture, we have started to deal with a very important problem of band theory of solids, and this is actually KP model. In fact, we have already discussed the basic concept of this KP model in first part of this lecture, and today we are going to see its second part. Actually, in this second part of the lecture on KP model, we will discuss the final result which we have obtained in the first part. And from the result in the first part, we have concluded that in solids there are allowed energy bands and the forbidden energy gap. But you will see that from the final result of the first part of the lecture, we can get all the properties of the electron moving in a periodically varying potential inside the crystal lattice. Okay, so this part is mainly the discussion of the final result of the first part of the lecture. Okay, so you must remember what was our final result in the first part of this lecture on KP model. You have seen in the first part that we have actually considered the behavior of electrons in a periodic potential, particularly in case of a one-dimensional crystal lattice. Okay, and the potential energy of the electron in that linear array of positive nuclei was assumed to have the form of periodic array of square wells. Okay, and then applying the after setting the Schrodinger equation for the two regions and solving it with the help of Bloch's theorem, finally we have obtained a particular result which I have mentioned here in this equation A. And this result was actually obtained by Kronig and Penney using the particular idea of Dirac delta function, that this result was obtained in a particular condition, that when the potential V naught tends to infinity and the width of the potential well B tends to 0. In this limiting condition, our result was like defined in this equation A. And you can see this result says that P times sine alpha A over alpha A plus cos alpha A equal to cos Ka. This was our final result. Actually, in this equation, this P is equal to beta square AB over 2. And you have seen that beta was this much. This was a square root of 2m V naught minus E over h bar square. But according to the assumption, V naught is tending towards infinity. It means V naught is much greater than E. So you can neglect in this limiting condition this E here, and so your result for beta is equal to this much. This is simply equal to a square root of 2m V naught over h bar square. Okay, and so this will be equal to when you will write beta square, this will be 2m V naught by h bar square, and substituting it here you will get that this P is equal to m V naught AB divided by h bar square. And what was our alpha? Alpha was actually a square root of 2me over h bar square. Actually, these alpha and beta both are related to energy of the electron and both are positive. Okay. In fact, in this equation, when you talk about this P, you have seen that P is actually the measure of area of the potential well, and this measures the strength of the potential well, that how much the electron is attracted or electron is bonded to the square well. This is measured in terms of P. So in fact, if P is increased, you have seen the electron is more strongly, more totally bound to the particular potential well. But when P is small, then the electron will be loosely bonded. And if you consider that this P is completely equal to 0, this refers actually free electron. And all these things we will see in this discussion. Okay. In fact, we will see that when we consider the values of P from 0 to infinity, what happens to the state of the electron, we can discuss. And this is our prime aim of this second part of the lecture on KP model. Okay. In fact, you have seen that when the LHS of this equation A, see here, this is P sine alpha A plus cos alpha A, when it is plotted in against of alpha A, the curve as shown in this figure are obtained. Actually, you have seen already the discussion of this figure in your previous lecture on KP model, that is in the first part of the lecture on this KP model. In fact, you can see this is the LHS of our equation, okay? And it has been plotted in against of alpha A. But in this equation, you can see the RHS is cos Ka, and you know cos Ka must always lies between plus 1 and minus 1, because cos theta is never greater than plus 1 and it is never greater than never less than minus 1. Okay. So it is obvious that a solution exists only for those value of energy E for which the LHS of this equation is between these two limits, that is between plus 1 and minus 1. In other words, you can say that there is a solution for the shaded region as I have shown, because this shaded region refers the region for which the value of this quantity in LHS is actually between plus 1 and minus 1. So there will be a solution for the shaded region as shown in this figure, but no solution outside of it. Okay. So, you know, since alpha is related to E, this means that the electron may possess energy within certain bands but not outside of them. In fact, in this figure, this shaded region represent the band in which electron exists. It means electron has such an energy which is possible and that can exist in this shaded region. Okay. But between two shaded regions, you can see there is unshaded region, and this region, in this region you can see that the value of this quantity which I have mentioned on this y-axis deviates from plus 1 and minus 1. Here you can see the value of this is less than minus 1, and in this region it is greater than plus 1. So at alpha A equal to pi, this is after this value, this cos alpha A or this LHS is less than minus 1, and at alpha A equal to 2 pi, it becomes greater than plus 1. So such a region is not allowed, or in other words you can say that electron cannot have such an energy so that it can remain in this region. So these are called forbidden region. So in this figure you have seen that the shaded region represent the allowed region or the allowed energy band where electron exists, and the unshaded region which is I am marking here, this is the unshaded region, this is unshaded region, this is unshaded region, this is unshaded region. actually no electron will exist in this region, because such an energy cannot be possessed by the electron. Okay, so this were the basic conclusion of this model, and we have seen this in the first part of the lecture. But as I have told you that in this present second part of the lecture, our aim is to discuss some interesting conclusions that can be derived from this result which I have obtained in the first part of the lecture. Okay. So let us see the different situations. Okay. In first situation, we consider that this V naught times B, which actually represents the area of the potential well, is large. And you can see from the expression for P that if V naught B is larger, then P will be large. Okay? And when P will be large, then what will happen? The electron will be more tightly bonded to the potential well. Okay? And in fact, in that condition, it is seen that the LHS of that equation A, that is this factor will cross the +1 value and the +1 to -1 region at a steep angle. You can compare these two figures. Here, this curve passes through the +1, this is the +1 point and this is the -1 point at a particular angle, but in this figure it passes through those 2 points, that is +1 and -1, at more steep angle. Okay, so what will happen when this curve will pass through the region from +1 to -1 at a steep angle? What will happen? Actually, in this condition, you can see the allowed bands will become narrow. The width of this shaded region, you can see this becomes smaller, or this becomes narrow. And on the other hand, the width of the forbidden region becomes wide. So here, this shaded region, I have shown that this shaded region actually represents the allowed energy band, and this becomes narrower, and this forbidden band, which is unshaded, I have shown here, this becomes wider. Okay, so when you will take the larger value of P, what will be the effect? The effect will be the allowed band will become narrower and the forbidden band will become wider. Okay, and this happens when P is taken large. Okay, our P will be large when this V naught times B is large. Okay, I think you are getting the things. Okay, now let us see an extreme condition in this second point. And in this extreme condition, we will consider that this P is tending towards infinity. It is not large, but very large, extremely large, so that you can say that P is tending towards infinity. Then what will happen? So, to know what will happen to the energy bands, both allowed and the forbidden, when we consider this limiting condition that P is tending towards infinity. So let us cast our equation A on the basis of which we are discussing our result in a proper form, so that we can know what will be the effect of this limiting condition P tending towards infinity on the allowed band and the forbidden band. Okay, so let us start from our result. Your result is P sin alpha A over alpha A plus cos alpha A equal to cos Ka. Okay, and so you can say that this P sin alpha A over alpha A is equal to cos Ka minus cos alpha A, and hence you can see this sin alpha A will be equal to cos Ka minus cos alpha A times alpha A over P. Okay, Now impose this limiting condition on this result, that our condition is what? This is P tending towards infinity. And you can see when this P in denominator will become infinity, then the result will in RHS will become 0. Okay, because you know, whenever we divide a finite number or quantity by infinity, the result is 0. Okay, so in this condition you can easily say that sine alpha A is equal to 0. So what will be the general value of alpha A? You know, when sine theta is 0, the general value of theta is plus minus n pi. Okay, and here alpha A will be equal to plus minus n pi. Okay, in fact here n is equal to 1, 2, 3 and so on. Actually, mathematically, when n is equal to 0, then this condition will get satisfied. But here we cannot take n equal to 0. Because if you will take n equal to 0, in that condition, in that very condition, the electron will be found nowhere. But we know electron is present here. So we can't take this n equal to 0. So mathematically that is all right, but physically that is not possible. So we can take n equal to 1, 2, 3 and so on. Okay. So alpha A in this condition when P tends to infinity is plus minus n pi. And so that you can say that alpha square is equal to n square pi square over A square. Okay. But you have seen that alpha square is equal to 2me over h bar square. But I have written here not E but En. Actually, this energy is for the electron in its nth state or nth energy level, you can say. So this subscript has been used here in E. So 2men over h bar square is equal to n square pi square over A square. And so from here you can easily say that what will be En? En is equal to n square pi square h bar square over 2ma square. Okay. After seeing this result, can you remember, have you studied this type of result earlier? Definitely you have studied. When I have dealt the problem of one-dimensional electron in one-dimensional potential box in free electron theory of metals, and also in my lecture in the playlist of quantum mechanics, then you have seen that when we take a free electron inside a one-dimensional potential box, then the energy eigenvalue of that electron is found like this. Okay, here A, which is actually the here lattice constant, or you can say this is actually the distance between two successive lattice points, that is equal to the width of the potential box. And this is the result for a free electron inside a potential box of width A. Okay, and as I have mentioned here that this En has been written at the place of E, and this is energy of the nth level. So in this condition, En is the energy level for a potential well of width A, and accordingly all electrons will be in this condition independent of each other. Okay, so in this condition you can see that an electron inside a potential well is confined to that potential well. It does not pass from one potential well to another. Okay, because in this condition electron will be most tightly bonded, because you have taken P tends towards infinity, and this is the situation that our electron is infinitely bonded to a particular potential well. So an electron inside a potential well cannot transmit to the another potential well. Okay, And in this condition you can see that this model agrees with the free electron model of our of metal. Okay, so you can say that in this condition electrons are independent of each other and each is confined to one atom by an infinite potential barrier. Okay, and in this case allowed regions becomes infinitely narrow. This is the main feature of this point. You can see in this condition what will happen if this is your allowed band. This line represents the allowed band, this line represents the another allowed energy band, this line represents the third allowed energy band, and between two these allowed band there are forbidden energy band or energy gap. So in this condition the energy eigenvalue spectrum of our electron becomes a line spectrum. Okay, so I have mentioned it here that you can see that that the energy spectrum then takes the shape of line spectrum. Okay, not band but line. And this is the idea of free electron theory of metals. So this band model actually explains the free electron theory. How? When there will be an extreme condition that this P tends towards infinity, then our energy bands, that is allowed energy bands, becomes just like energy levels, just like line having negligible width. Okay, and so in this condition our band theory agrees with the free electron theory, and this can explain all the features of free electron theory. Okay, now we will consider just the reverse situation. In second point we have considered that P is tending towards infinity, and this represents that electron is most tightly bonded to the potential well, and it is not free to move from one potential well to another. It is confined to only one potential well, only one atom or nuclei. Okay, but now we consider a completely free electron. When you say P is equal to 0, it means electron is not bonded to the potential well, not bonded to the atom. So this becomes just free electron. Okay, and you will see this the result of our band theory also explains this situation correctly. How? You can see from this result that when P becomes 0, when this P will become 0, this first term will vanish, this will be 0, and so this cos alpha A will be equal to cos Ka. So when you will take the limiting condition P equal to 0, then cos alpha A is equal to cos Ka, and so you can say that alpha A is equal to Ka, and so that alpha is equal to K, and hence you can say that alpha square equal to K square. But you know alpha square is equal to this much, this is 2me over h bar square. Okay, and that will be equal to K square. So E is equal to h bar square K square over 2m. But what is this h bar K? You know, momentum of the electron is given by h bar K, that is reduced Planck's constant multiplied by wave vector, that gives the momentum of the electron. So in fact you can write that this E is equal to P square over 2m, and you can see this is actually the kinetic energy of our electron. It means the total energy of electron becomes is equal to its kinetic energy. So its potential energy is 0, and if potential energy is 0, what does it mean? Physically it means our electron is completely free. So this is the expression for a free electron for its energy. Okay, so you can say that this is the energy of the free electron. And so after this you can see, when we have considered P tending towards infinity, then we have seen that the energy band becomes most narrower, allowed energy band becomes just like a line, okay, just like an energy level, okay, and forbidden energy gap is more and more wider, okay, and electron was most tightly bonded to the atom or the nucleus or the potential well. So that was the case of most tightly bonded electron. But when you take P equal to 0, you are taking a completely free electron, okay, and this result gives a valid result for these two situations, okay. So you can say that varying the value of P from 0 to infinity, we cover the whole range from the completely free to completely bound electron. When you take P equal to 0, the electron is completely free. And when you take P equal to infinity, the electron is completely bonded. Okay. So this is a very interesting, these are very interesting result, and you can see the result obtained in by this KP model explains all the quantum mechanical behavior of our electron inside this crystal lattice. Okay. I think this session is interesting to you, and you are watching the video very seriously. So if you will watch the video seriously, definitely you will get more and more benefit for your examination purpose and for your knowledge of solid state physics too. Okay. Now let us see a very important concept which I will discuss here, and see this figure. You can see at the boundary of this allowed energy band. See here, at the boundary of this allowed energy band, this LHS of that equation or RHS of that equation is equal to +1. Okay, and here it is -1. So you can say that at the boundaries of the allowed energy band, the value of cos Ka, that is its RHS, is equal to +-1. Okay, and if cos Ka is +-1, then this will be equal to cos n pi, and this n will be again 1, 2, 3 and so on. We can again not take n equal to 0, because although mathematically that is all right, because you know cos 0 is also +1, but that is not physically possible here, because that represents a completely unphysical state of the electron. Okay, that will not give a valid wave function, you can say. So n equal to 0 is restricted, and since cos Ka is equal to cos n pi, so you can say that Ka is equal to n pi, and so K is equal to n pi over A. Okay, K equal to n pi over A. Now let us see. I have plotted here a graph between the energy of the electron E and its wave vector K. So this is the graphical plot of E in against of K. Okay, and we will actually examine that this typical energy versus K plot gives a particular information, and what is that information? Let us see now. You can see this graph. According to this graphical plot, the curve is actually discontinuous at particular points. Here you can see this is the discontinuity. This dashed line represents the discontinuity. Again here we will get discontinuity. Here it is discontinuous. Here it is discontinuous. So you can see from this figure that there are discontinuities in the energy curve at what values of k. You can see it. Actually, you can see that this discontinuity exists at k equal to plus minus pi a, plus minus 2 pi a, and plus minus 3 pi a, and so on. You can see at this k equal to plus pi by a and minus pi by a, the curve is discontinuous. At k equal to 2 pi by a and minus 2 pi by a, the curve is discontinuous. And in the similar manner, you can say that this curve will be discontinuous at plus 3 pi by a and minus 3 pi by a. Okay. Actually, the dashed curve, here I have actually joined these two parts of the curve at point of discontinuity by the dashed curve. Actually, this dashed curve in the is the free electron parabola. Okay. And at the above values of k, that is at these values which I have mentioned it here, we get energy gaps. So at this free electron parabola, you can see I have shown that there is an energy gap which is called forbidden energy gap. I have mentioned it here. This undashed region is called forbidden energy gap. But for the values of k not near these energies, that is for the energy lying in this region, lying in this region, and for the energy lying in this region and in this region, the energy for these values of k, the energies are much like those of a free electron. Okay, and the origin of the allowed energy bands and the forbidden energy gaps are clear from this figure. You can see that this is the allowed energy band which I have shown by this shaded region. So all this shaded region represents the allowed energy band, and the unshaded region represents the non-allowed, or you can say the forbidden energy gap. Okay. So the allowed and forbidden energy regions can be exist inside our crystal lattice. That can be understood from this energy versus k graph. Okay, I think you have got all the informations regarding this. So I have mentioned it here. You can see that in this E versus k curve there are discontinuities at k equal to plus minus pi a, plus minus 2 pi by a, and plus minus 3 pi by a, and so on. The dashed curve is the free electron parabola. At the above value of k, we get energy gaps, whereas for values of k not near these energies are much like those of a free electron. And the origin of the allowed energy band and the forbidden energy gaps are clear from this figure. Okay. Now we will see how this energy band can be understood in terms of Bragg's law. This is a very important fact, particularly for competitive examination like civil services examination if your optional paper is physics. Okay. Actually, the occurrence of the gaps can be understood in terms of Bragg reflection of de Broglie waves associated with the moving electron through the lattice. So if a question is asked how you can explain the existence of energy band in solids on the basis of Bragg's law, how you can explain it? Actually, in this condition, we will have to consider that the quantum mechanical behavior of electron. You know, according to de Broglie hypothesis, a moving electron has a wave nature. A matter wave is associated with it. Okay, and in this term we can explain the occurrence of the gaps in the energy gaps in the solid. Okay, actually, you know, what is Bragg's law or what is Bragg condition for reflection of waves? I have already provided video, so many videos on Bragg's law earlier, and so I hope you have an idea of it. You know, according to Bragg's law, the reflection or the diffraction of waves takes place when this condition is satisfied. 2a sine theta equal to n lambda. Actually, earlier we have studied it is in the form 2d sine theta equal to n lambda, but here at the place of d I have written a. Okay, because here a is the spacing between the ions of a lattice. So I have replaced d by a. Okay, but our discussion is based on the motion of electron inside a one-dimensional crystal. Okay, so if we will consider the lattice only in one dimension, that is, let us say in x direction, then this theta will be equal to pi by 2. In case of one-dimensional lattice, this theta will be what? This will be pi by 2. And so this Bragg's condition for reflection can be written in this case as 2a equal to n lambda, because sine pi by 2 will be 1. But you know, this k, which is wave vector, this is equal to 2 pi over lambda. So lambda is equal to 2 pi over k. Okay, so instead of this lambda, you can write 2 pi over k. And so a is equal to what? This 2 and this 2 will cancel out, and a is equal to n pi over k. And so you can say that k is equal to n pi over a. Now again you can see here n is equal to 1, 2, 3 and so on. This actually represents the order of Bragg's reflection. N equal to 1 represents first order Bragg reflection or diffraction. N equal to 2, this is for the second maxima. N equal to 3 for the third maxima and so on. Okay, these are actually the order of maxima. Okay, so taking n equal to 1, 2, 3 and so on, you can say that the value of k will be equal to what? That will be plus minus pi over a, plus minus 2 pi over a, and plus minus 3 pi over a. Actually here n is not equal to plus minus 1, not equal to plus minus 2, not equal to plus minus 3, but we have taken here both signs. Why we have taken minus sign 2? Because this minus sign represents the wave traveling in negative x direction, while the plus sign represents the electron wave traveling in positive x direction. So in fact, when you talk about the wave associated with electron moving inside a crystal, the incident wave may be in positive x direction and it may be in negative x direction. So we have inserted here the sign of plus minus. Plus represents the incident wave which moves along the positive x direction. Okay, and minus sign refers the wave traveling in negative x direction. Okay, now if this pi by a, 2 pi by a, 3 pi by a and so on, these are actually the values of the k at the gaps of energy versus k curve. You can see in this figure. Here at k equal to pi by a, there is energy gap. You can see it here. Okay, at k equal to 2 pi by a, there is another energy gap. So the value obtained for k refers its values at the energy gap. And so this is why we say that the Bragg's reflection condition actually explains how this energy gap is created. Okay, or there will be energy gap inside a solid. In fact, the waves corresponding to values of k not satisfying this condition, all those values of k which will not satisfy this condition travel almost freely, that will be not reflected. Okay, but those values of k which will satisfy this condition are reflected, and due to its reflection there will be a superposition between the incident wave and the reflected wave, and so a standing wave will be created. So you can see that from this energy versus k curve, and with the help of Bragg's reflection condition or Bragg's law, we can see the occurrence of the energy gap in the inside the solid. Okay, so these were some interesting points which we have discussed in very detail in our this lecture regarding this Kronig-Penney model. So after this second lecture, in continuation with the first lecture on KP model, now this concept is completed, and I hope combining these two lectures your all ideas about the KP model has been cleared. Okay, thank you very much.